Hello, and welcome to this introductory video on EMF versus potential. In this video, we're just going to introduce what an EMF is and how it relates to the true potential in a circuit once you've connected this battery with some particular EMF. So EMF is actually something that's usually specified for batteries, and it is also this historical, unfortunate name. It stands for electromotive force. We don't really say that anymore, we just call it an EMF now because we realize it's not a force, it's actually a potential. So what is it supposed to represent? The idea is, if I've got a battery, and it's just kind of sitting here, so I'll draw it like a real battery, right, it's got its connector, and you were to measure that thing, what is the potential across there? When you say that's a 12-volt battery or 1.5 volt, AA battery, well, that is the EMF of that battery. That's the potential difference across the terminals when no current is actually flowing. Okay, so the difference between this and this is 12 volts. But once you start a current flowing, well, what's going to happen? So if I took a wire and I connected this really quickly across here, would the current actually be infinite because there's no resistance if we have sort of an ideal wire? The answer to that question is no. The current would not be infinite even if this wire is ideal, as long as this is a real battery, because in making a battery, there's going to be some sort of resistance in here. It might be small, and ideally it is, but there's always some resistance inside your battery. So if you call that resistance R, little r, that's the internal resistance of the battery, then what you realize is even in this ideal circuit, you've got some resistance happening here. And of course, we know that in order to overcome a resistance, you have to use up some of your energy, and that results in a potential drop. So once there's a potential drop, that then tells us exactly what we need to know, that if there's a drop by crossing this resistor, then now while there's this current flowing and I'm losing some of my potential across this resistor, when I measure from terminal to terminal, I'm not going to measure that 1.5 volts or the 12 volts or whatever that battery was supposed to be according to its EMF. I'm going to measure something smaller. Okay, so that's the difference. EMF is like the theoretical maximum that your battery could do. The real potential across that circuit, though, is basically taking into consideration the fact that you're losing some of your energy because of that resistance. So now, when you add in a real resistor into your circuit, so that your circuit is actually doing something useful, okay, and that has some capital R, then you can ask now what's going on in this circuit. Well, the EMF is giving rise to some current, but there is a resistance R and the internal resistance. And so what do we have? We've got resistors in series, they add. Okay, so that just means then that V, or rather the EMF, is going to be the current times the resistance, R plus R. And therefore, what do we have? We have that the current in this circuit is the EMF on R plus R. Okay, because that is the total resistance in our circuit. They're in series. And so we have this sort of expression for what's going on in terms of the current for this real battery that actually has some internal resistance. Now, usually, the internal resistance is small compared to the resistance of a circuit. That's the sort of goal. You don't want to waste most of the battery in just overcoming the internal resistance. So you want R to be small compared to R, which is why in general we don't really worry, and we just kind of assume that the EMF is basically the voltage in our circuit, and then we just go with IR. But in reality, this is what's going on, or this thing here. And the EMF is actually I times the total resistance, of course. And so you have that expression, and it's just something to keep in mind. The EMF is not really what you're ever going to measure in a circuit because there is always some small resistance. Now, the smaller you make it, the better you're doing, and the closer you're approximating the sort of thing that we normally write. But this is really an idealized case.